And now you can see these are the equivalent states. So we have two particles in alpha and one particle in beta orbital. And so alpha particle number one is in alpha, particle number two is in alpha state, and particle number three in beta state. Or we can say particle number two in alpha state and particle number one is same thing. So we can say this is an equivalent state. So these two are equivalent. These two are equivalent. And similarly, these two are equivalent. And so one can simplify, अगर equivalent है, so one can simplify, which is equals to 1 upon under root 3 factorial. And then we can write it 1 upon under root 2 factorial, because in fact 1 factorial is 1. And then we can write 2 times alpha 1, alpha 2, beta 3, plus 2 times alpha 1, alpha 3, and beta 2, plus 2 times alpha 2, alpha 3, and beta 1. Yeah. And then अगर मैं इसको simplify करूँ तो I could have 1 upon under root 3 times uh, alpha 1, alpha 2, beta 3, plus alpha 1, alpha 3, beta 2, plus alpha 2, alpha 3, and beta 1. So 2 common ले लिया. So this is now correctly normalized. कुछ चीज़ें इसमें you can understand. So अगर तीन particles हैं तो number of possible states जो है, number of possible permutations जो होंगी वो 6 होंगी. 6 is basically 3 factorial. अगर चार particles होंगे तो number of possible permutation जो हैं वो 4 factorials हो जाएंगे, and so on. And then bosons के लिए तो equivalent state हो सकती हैं अगर एक से ज़्यादा क्योंकि बोसॉन्स के लिए एक से ज़्यादा पार्टिकल के अंदर एक से ज़्यादा पार्टिकल्स एक स्टेट में हो सकते हैं, बट फर्मियंस के अंदर नहीं हो सकते हैं. बट यू कैन सी दैट दिस बिकम्स मोर कॉम्प्लेक्स इफ द नंबर ऑफ पार्टिकल्स जो है वो इंक्रीज करते चले जाएं. सो इस कॉम्प्लेक्सिटी को वी कैन रिमूव दिस कॉम्प्लेक्सिटी, और वी कैन सिंप्लीफाई दिस पिक्चर by considering a cat vector. So we can write here, in order to simplify the uh, क्या कहेंगे इसको, in order to simplify for n number of particles, we consider cat vector. We consider cat vector notation. और कैसे लिखेंगे? We could write for this cat vector as psi, and this is equals to n1 comma n2 comma n3 comma so on. So what are ni's? Ni's are the occupation numbers for the orbitals. यानी n occupation number का मतलब है number of particles occupying an orbital. So where ni are the occupation numbers for the orbitals. For the orbitals. मतलब क्या है? ऑक्यूपेशन नंबर से क्या मुराद है? ऑक्यूपेशन नंबर implies number of particles occupying an orbital is the occupation number. So it means this cat is understood to be properly normalized and symmetrized. And it is normalized and symmetrized regardless of whether the occupants are bosons or fermions. So the the ket vector is understood to be properly properly normalized, and symmetrized regardless of whether whether it is for bosons और fermions. दोनों के लिए इनफैक्ट होगा. So for bosons we can write we can think of Ni as 0, 1, 2, and 3. That is, uh, in fact, no particle or one particle or three particle or four particle and so on. So for bosons, Ni could be 0, 1, 2, 3, and so on. That is, no particle or one particle or two particle or three particle. जबकि for fermions Ni जो है या तो सिफर होगा, that is no particle, और one particle only. या सो या तो किसी स्टेट के अंदर कोई पार्टिकल नहीं होगा या एक पार्टिकल होगा. ठीक है ना. सो basically this is the case. Uh, in fact, n1 particles have some eigen value जिसको हम let's say in terms of अगर eigen value define करें, because the Hamiltonian operator would give you the energy eigenvalue for those orbitals as well. So then n1 particles would have some eigenvalue because of the operator. उस eigenvalue को k1 कहा जा सकता है. n2 would particles would have the same eigenvalue, which is k2, and corresponding to a complete set of this can correspond to all in fact operators from k1, k2, k3, and so on. So one can further say that uh, also in terms of eigenvalues, n1 particles have some eigenvalue value k1 corresponding to the operator k1 operator, and 2 have some eigenvalue k2 corresponding to operator k2, and so on. Yeah, so uh, this would means a complete set. So we would say leading to a complete set of operators k. complete set of operators K. So this is basically, in fact, the basic introduction to identical particles or multi-particle states. Now let's talk about occupation number and creation and annihilation operators, जो कि बुनियादी तौर पर इस मल्टी पार्टिकल सिस्टम और मल्टी पार्टिकल क्वांटम सिस्टम का के ऑपरेटर्स हैं. सो वी वुड स्टार्ट विद द ऑक्यूपेशन numbers, and we would also talk about creation oblique annihilation operators. So for this purpose, or for the purpose of calculation, um, it is important to invent, or it is very useful to invent operators that change the number of particles in one particle state. That is, change the number of particles in one particle state as to increase the number of particles in one particle state, or to decrease the number of particles in one particle state. So we would say, for the purpose of calculations, that is, in order to determine energy eigenspectrum, it is uh, useful to sort of invent operators that sort of change the number of particles in a state, particles in the one particle state. Yeah, so we would have two operator AI dagger operating on N1, N2, so on up till Ni, so on, which would be proportional to, rather equality नहीं, proportional to N1, N2, so on up till Ni plus 1. So this operator जो हम लिख रहे हैं, that is some operator which basically increases the number of particles in a state. So इसको हम कहेंगे creates one particle in a state. Similarly, there is an operator, उसको annihilation operator कहते हैं, AI. So N1, N2, so on up till Ni, and this is proportional to N1, N2, so on up till Ni minus 1. So this is basically destroys a particle, destroy one particle. Yeah. So AI dagger and AI, basically they change the occupation number of these state. Either they change the occupation number by one. Yeah. Uh, and so one would define them as, so AI dagger and AI change the occupation number only in the state with quantum number or numbers ki. So Ni hoga, so that would be change the occupation and number in ki. So uh, we could think about, before going into detail, so we could think about a vacuum state So zero state is a vacuum state, and all the states are zero. That is, all states have no particle. State with all with all Ni equals to zero. N is the occupation number. So if we have AI dagger operating on a state with 0, 0, 0, and so on up till uh, Ni equals to 1 हो जाएगा. So this would be 0, and this would give me a state with Ki. That is, only the state with the quantum number Ki is occupied with a particle. Why? Because we have AI dagger. And similarly, agar AI operator, annihilation operator is acted upon a vacuum state, it would give you 0 because there are no particles to destroy. Because there are no particles to destroy. So the operation of such an operator on a vacuum state containing no particles in any of these states would give you a 0. And once a particle is created, we can destroy it as well. So it means that once a particle is created, so you need to have a particle in a state to destroy a particle in that state. Yeah, is created. Once a particle is created, we can destroy that particle in that state. So if AI is operated on Kj, then this would imply AI operating on 0, 0, 0, so on up till Nj equals to 1, 0. Then this is equals to Kronecker delta Ij of 0, suggesting if I is equals to j, then obviously it would be a vacuum state. It would change into a vacuum state. And if I is not equals to 0, it would be 0. So यहाँ पर जो हम लिख रहे हैं delta ij, this would give you either 1 or 0. I equals to j पर 1 हो जाएगा, और I is not equals to j पर it would be 0. So it is in fact clear. If some annihilation operator is acted upon some state जिसका quantum number kj है, and if that quantum number, that particular orbital contains no particles, then this annihilation operator would give you a value which is equals to 0. जैसे यहाँ पर हमने बात की, it would give you a value 0. बट अगर AI पार्टिकल, AI annihilation operator operate करता है on some cat state whose quantum number is kj, and that particular state has one particle where and I is equals to j कर रहे हैं हम, then that would lead to a state which is a which is a vacuum state, that is a state with no particles in any of its orbitals. So these, we can say that these AI and AI daggers are basically defined in some basis, which is the Ki basis. From this, we can understand. We can also change our basis to some other basis. Then, how to change from one basis to another basis? We need to write some new type of operator. So these AI dagger, or rather पहले AI dagger and AI, they are defined in some KI basis. We could we can change the basis. We could have another basis, another another, let's say, complete set of of one particle states corresponding to basis, corresponding to another set of observables, let's say another observable set of observables, let's say उसका नाम हम L रख दें, let's say angular momentum with eigen value values L Q ले लें, ठीक है. Then there is basically there is some transformation from one basis to another, is another basis, इसको कहते हैं unitary transformation. That is a transformation जिसको हम back and forth कर सकें. You transform into another basis, and from that another basis you can come back into the original basis. Such transformations are known as unitary basis. और इसको कैसे लिखा जाता है? We could write it. So ki is the ket vector. We could transform from LQ basis to ki basis using so LQ, and then we have this LQ ki. Yeah. So you remember, this is the probability amplitude that you change from LQ basis to Li basis, or into some new basis. So this is into some new basis. Yeah. And we can also, so this is for this is some base, you have done you have done the change of basis, but you can also do the same operation for the creation and annihilation operators. And let's say we have new operators BQ dagger and BQ, जैसे वहाँ पर AI dagger and AI थे. Similarly we want to change from BQ dagger BQ to AI dagger and AI. So we could write similar sort of unitary transformation. So we have this unitary transformation for the change of basis. We can also have a unitary transformation from the change of operators. So we would analogously we have new creation operators, creation oblique annihilation operators. So अगर basis change हुए तो फिर हमारे पास operators भी change हो जाएंगे. So we would have new operators. Let's say वो new operators BQ dagger and BQ होंगे. और हम कैसे चेंज करेंगे? So we have AI dagger operating on the vacuum would give you summation over BQ. That would give me BQ dagger on vacuum. And then we have LQ KI. Yeah. So we can think about this zero is always to some state that is a state containing no particle. Yeah. So one could think about this is is always the the always the state with no particles. Yeah. So in fact, no particle state कहा जा सकता है. So we have changed, we have written how to change the bases, and then correspondingly how to change in fact their the creation and annihilation operator. So in a sense, this the equation is solved for transformation between A and B operator. So we can basically write some sort of a solution. So we can say sense, in a sense, the equation is solved for the the transformation between the A and B operators. और वो transformations operators, और वो क्या हो जाएगा? We could write it for AI dagger. AI dagger किसके बराबर हो जाएगा? That would be summation over Q, uh, PQ dagger LQ KI. Yeah. And similarly for AI, we would write summation over Q. This is AI and AI dagger are conjugate to each other, so then we would have AI LQ or BQ. Position of these operators is important. So uh, uh, these work for uh, यम अगर bosons के लिए कर रहे हैं तो they can also work for the fermions. So these work for 0 and 1 particle states as well. So इससे पहले आप बात करें any number of particle states, but यहाँ पर 0 and 1 के लिए भी हो सकते हैं. Then we suppose that the work for that is they in fact are equally suitable for multi-particle states and if this is true, then obviously we need to write some sort of a commutation relations for AI dagger and AI. And these commutation relations, they are sort of restrictions which are imposed on a quantum system. And so there would be different type or separate type of restrictions imposed on fermions and bosons. So for bosons, the restrictions or commutation relations would be commutation relations, and for fermions, the commutation relations would be known as the anti-commutation relations. Yeah. So this is very important conclusion from these. So these these work for these transformation equations. These rather लिख लें, these transformation equations work for 0 and 1 particle states as well. So then we suppose they work for multi-particle states as well. They work for multi-particle states. Yeah. और इसका consequence क्या हो जाएगा? What would be the consequence of this? The commutation the commutation relations of the AI dagger and AI are very much restricted, sort of very much restricted, restricted uh, to cases, to cases corresponding to bosons and fermions. Yeah, so there would be a sort of different type of restriction. इसका मतलब क्या है? This implies that the restrictions imposed uh, on bosons are in the form of commutators and restrictions for restrictions imposed on rather restrictions imposed on fermions uh, are in the form of anti-commutators. Anti-commutators. So this is a very important result जो हमें यहाँ से मिला. अब इस रिजल्ट को हम बुनियादी तौर पर मैथमेटिकली साबित करना चाहते हैं कि कम्यूटेटर्स और एंटी कम्यूटेटर्स होते हैं और इन एंटी कम्यूटेटर्स और एंटी कम्यूटेटर्स की मदद से देन वी विल प्रोसीड इन क्वांटम मैकेनिक्स फॉर द कैलकुलेशन ऑफ एनर्जी आइगन स्टेट्स.